All right, so I was asked to go over 1994. This question is free response question from 1994. It's a very good question. I don't know if you noticed, but a lot of the questions are just like this question, where the first part asks you predict the sign of entropy, and then delta G and delta H. So all of these things kind of come into play here. Okay, so the first thing here, we have this reaction. The delta H for this reaction is negative 145 kilojoules. Okay, predict the sign of the standard entropy for the reaction. Explain on the basis of your prediction. Okay, so let's think about this. If we look at the moles of gas, so delta S is standard entropy. It's the disorder of the system. Okay, the disorder of the system. So whatever side has the most moles of gas will have the greater entropy. And you know that entropy is, so overall entropy of the reaction is equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. Products minus reactants. Okay, so the products here, let's just say it has a kind of general entropy of 2, because it has 2 moles of gas. Now this is not exact, this is just kind of an estimate. And then the product here has a entropy of 3. So 2 minus 3 is negative 1. So the entropy is negative. It's not equal to negative 1. It's not equal to negative 1. It's just going to be negative. There's less disorder as you go from left to right. Okay, so the overall entropy is negative, and that's what I said here. Since the number of moles of gas decrease from reactants to products, it's going to be negative. Okay, because those products. Oh, did I say that wrong? Yeah. Oh no, I said that right. It's products minus reactants. So products has 2 minus reactants is 3. So you get a negative entropy. You get less disorder. Okay. Letter B. It says here, for the forward reaction, it is spontaneous. So as it moves from left to right, it's spontaneous. What change, if any, would occur in the value of delta G for this reaction as the temperature increased? Explain your reasoning using thermodynamic principles. So when they say using thermodynamic principles, I just simply use the equation. So this is the equation right here, delta G equals delta H minus T delta S. We know that delta H is negative. We know that delta S is negative. As T increases, this term here, this negative T delta S, becomes more and more positive. Okay, which would mean that the delta G would become less and less negative, or it would become less and less spontaneous. And again, don't use spontaneous. Actually, it's less thermodynamically favorable. So you're going to see a lot of these old questions ask about spontaneity, and they just nowadays they replace it with thermodynamically favorable. So anytime you see spontaneous, it would be so not spontaneous, it's thermodynamically favorable. So what change to the thermodynamic favorability would occur for a delta G? So as temperature goes up, delta G we become more and more positive. So delta G would become more and more positive, and it would become less thermodynamically favorable. Okay. Next one, what change, if any, would occur in the value of the equilibrium constant? For for the situation described in B. So basically, as temperature goes up. So as temperature increases, the equilibrium constant will become smaller, since it would shift towards the reactants. So if you think about it, the equilibrium constant is products over reactants. If we're increasing the temperature and it's becoming less and less thermodynamically favorable for the reaction to occur in the forward direction, it's going to want to occur more and more in the backwards direction. Okay, so you're going to have less and less products, more and more reactants, right? So the equilibrium constant, the reactants will go up, products will go down, therefore K will go down. Okay. You could also use the Ratlink equation, delta G equals RT ln of K, to figure it out too, like to show that, but I like this explanation better. Okay, for letters, I like this explanation better. I think it's easier. Okay, you could use Ratlink. You could also say that as the reaction is exothermic, so as temperature goes up, it's going to shift left as well. Okay, so you could also say that because you're adding temperature to the products, it's going to shift from products to reactants according to Le Chatelier's principle. This is Le Chatelier. So there's a lot of different ways you could word this to get points here. Okay, and then the last one, the absolute temperature at which the forward reaction becomes non-spontaneous can be predicted. Write the equation that is used to make this prediction. Okay, so that would mean delta G equals is 0, right? Because it's not negative, it's not positive, it just is 0. And why does this equation predict only an approximate value for the temperature? So here, if delta G equals 0, then T equals delta H over delta S. This is only an approximate temperature, approximate, because delta H and delta S vary slightly with temperature. Okay, so this would not be exact, but it's good enough. It's going to tell us a close enough temperature. And actually, James had a really good question about 2006B, because we do use this to actually, we use this equation later on, and the delta S at 298K to figure out what T is. And it's like, why would you use 298K if it's not at that temperature? Well, we just use it because delta S and delta H only vary very slightly. They only vary slightly at different temperatures. It's very, very slight. And the only time delta S and delta H really vary like largely is when you have a change in phase. Okay, so if this if the things went from like a gas to a liquid, or a gas to all the way to a solid, or a solid to a gas, or something like that, that would have big delta S or big delta H changes. However, if it's staying in the same state of matter, it's only going to be a very minor change, and we can use this equation to approximate the temperature at which we get equilibrium. Okay, it's going to be an approximate. It's not exact, it's approximate. Okay, again, because delta H and delta T do vary slightly with temperature, but not enough to make a huge difference. Okay, it's not enough to make this unacceptable. This is good enough for what we're doing. Okay, so hopefully that answers all your questions about this problem, as well as kind of clarifies that this is also from, again, 2006B, that question, where we use this delta H delta over delta S equals delta is T, and we're finding T, but we are using delta H and delta S at 298. Doesn't make sense, but because, again, these only change slightly temperature, we're okay, and we can find an approximate temperature. Okay. Hopefully that answers your questions. Please let me know if you need me to go over any other ones.